Hello, everyone. Welcome to our April presentation with 5 Star Chemicals. I'm Erin Hamrick, the marketing manager here at 5 Star. And today we have a wonderful guest, John Palmer, as many of you know. Just a couple of housekeeping things to go through, and then we'll get ready for the presentation. As you can see, there's a chat on the right. You can say hi, talk to your fellow attendees, say where you're from. That'd be great to hear. And then this presentation is recorded. So everyone knows this is recorded. We will send out a follow-up email to all attendees and people who signed up for it tomorrow with the link for the recording. It'll also be on our YouTube channel for 5 Star. And then if you are part of this Crowdcast platform, it'll be available on that as well. So just so everyone knows, this will be recorded so that you can go back and reference it. Another thing is if you do have a question, please use the Ask a Question prompt at the bottom of the screen. There you can vote other questions up so that he can answer those earlier. And we will get to those at the end of the presentation with the Q&A. So without further ado, I will turn it over to John.
Wow. Well, thank you very much. And it's a real pleasure to be here. I'm really gratified to see how so many of you attending. For what is a very dry topic. And my hope today is to help you understand water in perspective, how important it is, why it's important, when it's important, and where it ranks in the grand scheme of things. So let's dive in. Folks. Okay, why do we adjust brewing water? The first reason, number one reason, is to hit our target mash pH, which is in the range of 5.2 to 5.6. Second, to improve beer flavor. What do we adjust? Well, we adjust the mineral composition of the water, not the pH. How do we adjust it? We do that with salt additions, acid additions, and ion removal processes such as reverse osmosis. There are two groups of ions in water that we are concerned with. The first are those that affect pH, and these are calcium, magnesium, and bicarbonate, otherwise known as total alkalinity. Also, we are concerned with those that affect flavor, and these are sulfate, chloride, and sodium. Now, from a brewer's point of view, in terms of mineral concentration, 0 to 50 ppm is low. That's a low concentration. 50 to 100 is medium. 100 to 150 ppm is high. And over 150 ppm tends to be a problem, okay? And again, ppm equals parts per million or milligrams per liter. Before you can adjust your water, you need to know what your source water is. It's either surface water or groundwater, or it could be a blend. Surface water is generally low in minerals, but often high in organics. Organics being algae, dead fish, leaves, frogs, that kind of stuff. Could be chemicals as well from contamination, pollution. Surface water often requires carbon filtration to remove these off flavors and odor compounds. Okay. Groundwater, on the other hand, is often high in minerals, but typically low in organics. Often it's potable right out of the ground. But it often is very high in alkalinity, which needs to be reduced before it can be used for brewing. And this can require ion exchange, like softening, or reverse osmosis to reduce alkalinity. Important to know how your source water is disinfected. Does it use chlorine or chloramine? Chlorine will evaporate while you heat the water. Chloramine will not. Chloramine is chlorine that's been reacted with ammonia and makes it more stable. The best way to remove chloramine, and chlorine for that matter, from your brewing water is chemically. You can use sodium metabisulfite, which produces a little bit of chloride and sulfate in your water, like 10 ppm, or ascorbic acid. vitamin C. And vitamin C takes it out very quickly too. Other thing to know is, does your source water change throughout the year? Here in California, where we're in drought situations all the time, our source water can change weekly. And therefore, lots of California brewers turn to reverse osmosis systems so they can always start from ground zero and build up their water profile. So, if you're on the East Coast, somewhere nice like Asheville, then you really don't have that problem. You have a very steady water source that you can rely on. But again, important to know if your source water changes during the year. Here's some water sources comparison. And you can see here for Seattle, there's my cursor, over here at Seattle. Seattle is primarily precipitation, just fresh from the sky. Very low mineral, 8 calcium, 1 magnesium, very low alkalinity at 22, 1 sulfate, 4 chloride, 2 sodium, 5 silica. Total dissolved solids, TDS, of like 43, really low. This is functionally equivalent to reverse osmosis water. Okay, Mississippi River, higher calcium, 40, higher magnesium, 25, total alkalinity of 180. A little bit surprising, but picks up a lot. Water sources pick up what they flow over. But low sulfate, chloride, and sodium, TDS, less than 500. Lake Michigan, likewise, about 40 calcium, lower magnesium, 100 alkalinity, again, low sulfate, chloride, and sodium, low TDS. You go to some groundwater sources, such as San Diego, similar calcium, similar magnesium, similar alkalinity, but your permanent hardness, your sulfates, chlorides, and sodiums are much higher, with the TDS closer to 500. Lafayette, Indiana, high calcium, which is nice, high magnesium, which is nice, but very high alkalinity, which is bad. Sulfate and chloride and sodium are pretty good, manageable, TDS of 575. Madison, Wisconsin, good calcium, good magnesium, really high alkalinity that makes this water essentially unbrewable. You really can't get rid of this much alkalinity without absorbing the flavors of the acids that you use. So yeah, not good brewing water. All right, so that in mind, move on. Let's talk about water hardness. Hardness is simply the sum of the calcium and magnesium in the water. And this is typically measured as calcium carbonate, which is a measure of how readily that this water will form carbonate scale on your plumbing or clog the water company's pipes. Okay, hardness is actually composed of all of the cations, the metal ions dissolved in water, but calcium and magnesium account for 99% of all metal ions in the water typically. So those are the two we always focus on. As brewers, we want calcium and magnesium in our water. It facilitates lowering the mash pH and good yeast health and flocculation. We talk about two types of hardness. Permanent hardness, this is calcium and magnesium that are dissolved from sulfates and chlorides, high solubility salts. And we talk about temporary hardness. This is calcium and magnesium that are dissolved from bicarbonate and carbonate, low solubility salts. And soft water is simply not hard, okay? Soft water has low concentrations of calcium and magnesium. It doesn't say anything about alkalinity in the water. Alkalinity, the total alkalinity, is the sum of the carbonate species that are in the water. These are typically dissolved from limestone. And total alkalinity is a chemical measurement by titration, how much acid is required to reach a pH endpoint. Alkalinity, if you think back to the previous slide, is roughly equal to the temporary hardness of the water, because temporary hardness is talking about the calcium and magnesium that are dissolved from bicarbonate. So the amount of bicarbonate in the water is roughly equal to the total alkalinity. It's like 90 to 95% depending on the pH. So this is why we say we want to get rid of temporary hardness in our brewing water. It's not that we want to get rid of the hardness, it's what we want to get rid of the alkalinity that's associated with that hardness. Okay? And the reason is that alkalinity buffers or raises the mash pH, makes the beer less acidic and duller tasting, and can lead to astringency. Talk a little bit about the ions. Calcium, the most important ion in brewing, it's a cofactor for lowering mash pH via residual alkalinity. It is important in protein coagulation, trub formation, yeast metabolism, flocculation, and beer clarity. Generally, we talk about 50 ppm being the minimum level in the water and wort for good beer clarity. 100 to 200 ppm is better for good pH stability during lautering and better beer clarity. But over 200 ppm tends to taste minerally, tends to give you a dry, very dry, minerally finish in the beer. Magnesium is the sidekick of calcium. It's half as effective at lowering mash pH due to higher solubility, but it is a very vital yeast nutrient. The yeast typically need a minimum of 5 ppm in the wort for the good yeast health and metabolism. And an all malt wort will typically supply about 70 ppm to the wort. But from a yeast cell's point of view, if there's lots of calcium and just a little bit of magnesium, they're going to have a hard time seeing that magnesium. So we need to maintain some sort of parity between calcium and magnesium so that the yeast can readily get to it during fermentation. Okay, and so we talk about magnesium levels should be roughly 40% of the total. Recommended levels in brewing water are anywhere from 0 to 40 ppm, depending. If you go over 80 ppm, the beer starts taking on kind of a sour, bitter character. Perhaps you're familiar with Phillips Milk of Magnesia. Dark beers do seem to benefit from having like 30 ppm in the water, promoting a rounder dark beer flavor and better fermentation. Okay, total alkalinity is calcium carbonate. This is very often the villain. It keeps the calcium in check. Generally, your alkalinity should be low in your water. And like I said earlier, bicarbonate is generally about 95% of the total alkalinity. Alkalinity drives the mash pH up. It can lead to astringency from tannin and silicate extraction. It can result in a very coarse bitterness from your hops. But it is there and is useful for providing balance for darker, more acidic grain bills, because regardless of beer style, we want to be in that 5.2 to 5.6 pH range in the mash. Recommended range, depending on beer style, is anywhere from 0 to 120 ppm as calcium carbonate. 200 ppm maximum is about the most that you can work with for most brews. Any more than that, and you can't reduce it sufficiently without affecting the flavor of the beer. Okay, moving on to the flavor ions. Sulfate. Sulfate accentuates hop character, helps dry out the beer finish, but it can taste minerally and in conjunction with high concentrations of the other ions. 100 to 200 ppm in pale ales and IPAs tends to improve the hop character and finish, kind of drying out the beer, making that hop character more assertive, but also fading faster from your palate. However, sulfur is generally not desired in German lagers because the noble hops, the landrace hops used in German lagers, tend to have some sulfur character as well, and so high sulfur makes these otherwise light and floral, spicy hop characters more dank, which dank doesn't really work in lager unless you just love dank. Anyway, recommended range for sulfate is anywhere from 50 to 300 ppm for most styles. We talk about Burton-on-Trent and high sulfate, but 300 ppm is that really about the maximum you'd want to use in a beer. Otherwise, the beer just becomes too dry. Chloride is the counterpart to sulfate, and it tends to round out the malt character of the beer, making that malt character rounder, fuller, sweeter. Generally, we're looking at anywhere from 50 to 150 ppm for most styles. If you go over 200 up to 300, then you really start impacting beer clarity and stability. Beer flavor starts turning salty, and you can really impact your yeast health and the corrosion resistance of your stainless steel. So high chloride is not recommended beyond 200 ppm. Sodium is kind of along for the ride. Sodium chloride, sodium bicarbonate, sodium hydroxide. Once it's in water, it's kind of hard to get out, but you can remove it with reverse osmosis. Recommended levels are generally less than 100 ppm, although if you are brewing a light beer, low alcohol, low calorie beer, more sodium in conjunction with the chloride can help boost the malt flavors in a light beer, and make that a fuller tasting beer. And so 100 ppm, it's a guideline. If you go over 150, the beer can start taking on a little bit of a salty character, although people's sensitivity varies. Okay. Sulfate to chloride ratio. Okay, it's a good way to think about the overall character and flavor balance of your beer. Dryness versus fullness. We talk about the ratio, but it's important to understand that 40 to 10 is not going to taste the same as 400 to 100. All right. Useful range for sulfate to chloride ratio is anywhere from 5 to 1 down to a half to 1. Of course, maximum suggested sulfate, 300, 400, 500. I think 500 would be an absolute maximum. Maximum suggested chloride is 200 ppm. Colin and I recommend that you don't exceed 500 ppm for a combined sum, because now you start getting into that minerally realm. In terms of comparing regular West Coast IPA to New England IPA or hazy IPA, for West Coast, 250 sulfate to 50 chloride would be a typical ratio. For hazy IPA, the other way around, 150 chloride to say 50 sulfate would be typical. The water pH is not important. So often I get brewers talking about and worrying about their water because their water pH is 8.5 or 9. But the water pH is not important. What's important is the mineral content of the water. Okay? pH is essentially a measure of chemical equilibrium, the balance of hardness to alkalinity. So higher pH really just means that there's more alkalinity than hardness. You can have a low mineral water with the same pH as a high mineral water, but those two waters will affect the mash differently. Okay? Mash pH drives beer flavor, but mash pH drives beer pH, and beer pH drives beer flavor. That's what's important. To know what's in your water, I recommend the Brew Lab from Lamont. very reliable, easy to use test kit. I encourage you to get one with a digital pH meter, and so be aware that's out there, available from most of your homebrew suppliers. Also, I have my own water adjustment app. Easy to use, full instructions. It's free on the Google Play and Apple stores. So I'll let you know that's out there. It can help you calculate your mineral and acid additions to adjust your water. So how does water affect beer flavor? Okay. Well, the residual alkalinity of the water helps drive the mash pH. The mash pH drives the beer pH, and the beer pH drives beer flavor expression. Okay, we're going to talk about that more in a minute. Secondly, you have the seasoning balance, the sulfate and chloride. More sulfate makes that beer drier, makes the hop character more assertive. More chloride makes that beer character rounder, fuller, and sweeter. Then we talk about the seasoning level, the total dissolved solids, how much mineral is in the water to support the beer's flavors. Now, because we are typically adding calcium salts to adjust our water, the total dissolved solids is proportional to our calcium salt concentrations. Okay, we'll talk more about that later too. The effect of beer pH on flavor. In general, a lower beer pH focuses and brightens the malt and hop flavors. This is beneficial in your single malt pale beers, like your light lagers and your pale ales, where you predominantly have one malt that's supplying all the malt character. A little lower beer pH helps focus and brighten that malt character. Now in dark beers, where you have more specialty malts and some roast malts and so on, this focusing tends to result in kind of a singular roast character, and the beer tends to lose a bit of complexity. Okay, so in general, a higher beer pH broadens and opens up the malt and hop characters, and this is better for your multiple malt dark beers. Pale beers, if you open them up too much, tend to become dull and harsh. Okay, again, high beer pH tends to result in higher hop isomerization and kind of a different hop character. So, all right, second thing, seasoning balance, sulfate and chloride again. Dryness versus fullness, hoppy versus malty. I've said a lot of this already. Remember, you don't want to try to make a beer both malty and hoppy at the same time. It really ends up tasting minerally instead. Total dissolved solids, the light versus heavy seasoning aspect. If you think about these three beer styles, Bohemian Pilsner, German Pilsner, Dortmunder Export, very similar recipes, but different beer styles. And the water TDS, the structure, is one of the factors that makes these beer styles different. So Bohemian Pilsner with very low TDS, low mineral, tends to be a rich, malty beer, but with a large soft bitterness, okay? Soft flavors, soft malt and hop flavors. Whereas German Pilsner, with a little more mineral character, tends to be more crisp and a little bit more bitter, with a cleaner finish. And then you move to Dortmunder Export with an even higher total dissolved solids, more mineral in the water. This is actually a lower gravity style than the other two, but it doesn't taste like it. And that's because of all the mineral helping to support the beer's flavors. Okay? So that's the effect of mineral structure on beer flavor. Okay, residual alkalinity. So residual alkalinity is the difference between the effects of total alkalinity and hardness on the mash pH. There's the equation for total alkalinity minus the calcium plus half the magnesium divided by 3.5. That 3.5 factor depends on the water to grist ratio, degree of crush, things like that. It is not exact. It is useful as a concept, though, to help us understand the different effects of hardness versus alkalinity. Calcium and magnesium, the hardness, react with malt phosphates to produce hydrogen ions, and these hydrogen ions lower the mash pH if there is sufficient calcium in the water. And there's the equation there. That'll be on the quiz later. And there, so memorize that. Mash pH is the equilibrium between the water chemistry and the malt chemistry. The effect of water chemistry in the mash is summarized by residual alkalinity. Okay, the calcium and malt phosphates react to lower the mash pH, and alkalinity buffers that reaction. The other side of the equation is the malt chemistry, and your malts are either alkaline or acidic relative to your target pH of 5.2 to 5.6. Your base malts are generally alkaline. They have a distilled water mash pH of greater than 5.6, generally around 5.8. Your specialty malts, on the other hand, are generally acidic with respect to your target pH range. They're generally less than 5.2. Okay. So in terms of arriving at your mash pH, think about balancing a triangle. You have the base malt alkalinity times its weight, specialty malt acidity times its weight, and the residual alkalinity of the water times its volume. These three factors combined come together to arrive at the mash pH. All right? It's a good concept to understand when you're planning your recipes and planning your water additions. Now, interestingly, residual alkalinity has increasing effects that depend on the water to grist ratio. So here's a graph I did a number of years ago with a lot of data points for both Pilsner malt and North American two-row base malt. Water to grist ratios of 8 liters per kilogram, which is 4 quarts per pound, 6, 4, and 2. 4 quarts or 4 liters per kilogram equates to 2 quarts per pound. That's a pretty typical mash ratio. Here's 1 quart per pound here. So most people are going to be in this regime. What you can see is that you increase the residual alkalinity of the water from 0, which would correspond to either distilled water or equal hardness and alkalinity. You can see that there's an increasing rise in mash pH from 5.8 here at a water to grist ratio of 2 quarts per pound, 4 liters per kilogram, up to 6.2 in this case, at very high residual alkalinities. And it goes down as you go below into negative residual alkalinity. In other words, more hardness than alkalinity in the water. Last weekend, I was doing a collaboration brew in Mexico City, and we were doing a West Coast IPA recipe, predominantly Maris Otter, and which typically has a base malt mash pH or distilled water mash pH, of 5.8. It took an equivalent of negative 200 residual alkalinity to bring that mash pH down to 5.3. Okay, so just another data point for you. And that was at a water to grist ratio of 3 liters per kilogram. So right in the middle here. Oops. All right. So water to grist ratio versus residual alkalinity. The chemical equilibrium, the pH, between the water and the malt depends on the water to grist ratio. Lower water to grist ratio means less effect of the water on the mash pH, whereas a higher water to grist ratio means a greater effect of the water on the mash pH. And one thing to think about is that when you're planning your mashes and your sparges to get your, the wort that you want for your beer, a lower water to grist ratio in the mash translates to a higher first runnings gravity, but you're going to have to sparge with more water to get your total boil volume typically. And if that water has high residual alkalinity, your runnings pH is going to rise, and it could lead to astringency. Whereas if you have a little higher water to grist ratio and sparge with the same water, there's going to be less sparging overall and less pH rise. I typically like to brew with a higher water to grist ratio of at least 4 liters per kilogram. That way I'm achieving the same mash pH target as, in a lower water to grist ratio, but because of the higher water to grist, I'm getting a lower gravity wort, but more of it, and I have to do less sparging to hit my target volumes. So, but there's many ways to skin this cat. All right. The mash pH sets up the beer pH. I love this quote. The key point for control of pH throughout the brewing process is during mashing. This is due to the major influence that can be exerted at this stage on the content and format of the buffer systems that will operate subsequently in the wort and beer. Okay? Your beer begins in the mash. Keep that in mind. Let's talk a little bit more about pH. It is, of course, the concentration and activity of hydrogen ions in the solution. But it is better to think of it in terms of a measure of chemical equilibrium, especially in brewing. And in brewing, the pH of the wort, of the pH of the mash, the pH of the wort, the pH of the beer tells us how the brewing process is proceeding. Okay? A good analogy is noise. For those of you with children, you can monitor your children in the next room by listening to the general noise level. If that noise level changes, it's time to go check on them. Well, it's the same with your beer. If you monitor your pH throughout the brewing process and you see that pH change, then it's time to, it's time to check your process because something has changed. Something has changed in your brew. It's important to understand that pH physically, chemically changes with temperature. The pH of the solution is a measure of the chemical equilibrium. And as you change the temperature, that equilibrium, the activity of the molecules and atoms in solution is going to change as well. Okay? And if you think about it, different worts for different beer styles will have different amounts of buffering, different compounds in them. So the amount that pH changes due to changes in temperatures is going to be different between different styles. Generally, we talk about a wort pH change of about 0.3 between room temperature and mash temperature, but that's based on a pale wort, base malt only wort. When you start adding in specialty malts, then that's going to change a bit. So as a result, we always, as brewers, measure wort pH and beer pH with respect to room temperature. And that's captured in the ASBC methods of analysis, beer number 9 for pH. Most modern pH meters have automatic temperature compensation. The purpose of ATC is to keep that pH meter calibrated. So if you think about it, you go into the lab in the morning, you calibrate your pH meter, and you're calibrating it at room temperature with the 2 buffer solutions. It is now calibrated at room temperature. You take that pH meter over to a sample of wort. Let's say that wort sample is at 90 degrees Fahrenheit or 35 degrees Celsius. The ATC keeps the electrode in the meter calibrated so it gives you an accurate reading of the pH at that different sample temperature. It doesn't compensate for the actual change of pH due to temperature of the solution. So again, we, as a general rule, measure pH on room temperature or near room temperature samples. If you're at, 90 degrees Fahrenheit, 35 degrees Celsius, that's close enough to room temperature. You've changed the pH by less than half of a hundredth, or it's a very small amount. But when you're talking about 120, 150 degrees Fahrenheit, like approaching mash temperatures, now you're talking greater differences. What is the optimum mash pH? Well, it depends. There are like 30 different enzyme groups active in the mash at any one time, and so getting them all to optimize on a particular parameter, such as yield or protein breakdown or starch conversion, that's like herding cats. Okay. And so when we talk about optimum mash pH, we're generally talking about yield. And this represents a compromise between many different enzyme groups to get that optimum yield. The amylases generally prefer a pH between 5.5 and 6, but studies have shown that, and it's documented in Malt and Brewing Science, that when the mash pH, or the wort pH, I should say, exceeds 5.8, this tends to promote astringency, the solubilization of tannins and silicates from the grain husks. So therefore, we tend to brew at a lower mash pH to generate a lower wort pH in the region of 5.2 to 5.6 and avoid this astringency. Okay. My co-author, Colin Kaminski, in the Water book, was intrigued by experiments that we've done over the years where we could taste the difference between beers that had been brewed at different pHs. And so he went back to his tasting notes and brewing records and found this correlation. His boil pH affected his hop expression. At 5.4, he felt that the hop expression was a bit strong and harsh. At 5.2, it was just right. 5.0, it was a little bit weak. In terms of beer pH and flavor, he found that his tasting notes reflected that beer pH of 4.4 caused that pale ale to be a bit soft and soapy. 4.2 is just right, and 4.0 was rather sharp and crisp. Okay, so yes, a 0.2 change in beer pH can have a noticeable effect on flavor. And this sort of experiment is one I've done several times, several breweries over the years, and you can even see it replicated on Brewlosophy as well. So good to know. Suggested mash pH guidelines, okay? Not rules, guidelines. For pale beers, you tend to want a little lower mash pH, which will then translate, hopefully, into a little bit lower beer pH. So 5.2 to 5.4 to help brighten that malt character. Amber beers with some amount of specialty malts helping keep that mash pH down. You're looking for somewhere 5.3 to 5.5, achieving a little higher pH than the pale beers, but helping to keep that malt character open. For your dark beers, we go a little higher, 5.4 to 5.6, trying to open up that malt character a little bit more, allowing you to taste the different specialty malts, but still maintain no astringency and good conversion. Again, water pH is not important. Different waters can have the same pH, and if you try to adjust your water based on pH, you're generally putting the cart before the horse. You're doing it backwards, okay? Adjust your water based on its mineral content, not its pH. When and how do we measure pH? Your mash pH is your first priority, and so we are looking for that mash pH of 5.2 to 5.6 at room temperature at the beginning to ensure good saccharification, good starch conversion. I like to dough in, thoroughly mix the grist with the water, and then wait 5-10 minutes for it to homogenize, for compounds to really be released, and that pH to stabilize a bit. So about 10 minutes into the mash is when I'll pull a sample from the top, and pour that into a shallow saucer so to help it cool, and then measure it with the pH meter. If you have sufficient calcium, and you think back to that calcium malt phosphate reaction, the mash pH, this reaction will continue to occur during the mash, during the hour-long mash. So pH will continue to fall, and we're going to talk more about that in a minute. We're looking for this 5.2 to 5.6 range at the beginning of the mash, all right? And finally, if at first you don't succeed, try again tomorrow. Today's malts are so enzymatically strong that conversion is really happening, even if you're not at the right mash pH. Maybe, the conversion is not going as well as it could, but there are other compounds that are also being affected. Going back to the quote that began the thing, the key point for mash control, brewing control. So if your mash pH is high, yes, you can add some acid, try to bring it down. If your mash pH is too low, you can add sodium bicarbonate, baking soda, to try to bring it up, but it's going to take a while. It's going to take maybe 20-30 minutes for that pH to rise. Calcium carbonate will not bring it up fast enough. It takes about 2 hours for it to happen. So again, adjust your water, try again tomorrow, is my best advice. All right, so here's a diagram showing how mash pH sets up the beer pH. We start out in the mash with between 5.2 and 5.6, and during the mash, if there is sufficient calcium, the pH may drop by about another 0.2. So we go into the boil, typically at around a pH of 5.0. During the boil, protein coagulation is happening, evaporation is happening. pH tends to drop by about another 0.3 during the boil, up to 0.3. Going into fermentation, the yeast are taking in amino acids, they're excreting organic acids and protons to maintain their cellular chemistry. Fermentation is a great pH leveler, and pH tends to drop by about another 0.5 during fermentation. And this is how we get from our mash pH range of 5.2 to 5.6 down to our final beer pH range of 4 to 4.6, style dependent, of course. So this is a good diagram to help you understand the progression of pH during the brew, and it's a good tool for monitoring the quality of your brews if you're brewing the same recipe, week in and week out, like professional brewers do. Anytime you see this pH progression change significantly, more than 1/10 or so, it's time to look at your process and see what might have gone wrong. Maybe it's a different ingredient lot, maybe it's some caustic that got left in a tank by mistake. It could be several things, but the pH really should not deviate much for the same recipe if you're doing it consistently. Optimizing beer pH for flavor. Okay, every beer recipe has an optimum beer pH, generally in that range of 4 to 4.6. Every beer recipe should have a range of a portfolio of malt flavors and aromas, hop flavors and aromas, and yeast flavors and aromas. If you can't taste or smell everything that you're putting into that beer, then you may not be at the right beer pH. So I suggest you go back up to the mash, adjust the pH up or down, and allow that change to trickle through the process to change your beer pH and see if that doesn't improve the flavor character of your beer. Again, suggested mash pH guidelines: pale beers 5.2 to 5.4, amber beers 5.3 to 5.5, dark beers 5.4 to 5.6. Again, water pH not important. It's mash pH, wort pH, beer pH, not water. Okay, now let's move on to talking about adjusting water for style. We've talked a lot about the science. Let's now talk about the practicalities. If we define a beer style by 3 parameters: beer flavor balance, beer color, and beer structure, malty, balanced, or hoppy, pale, amber, or dark, soft, medium, and firm, then we can choose a water to facilitate that beer style. And in terms of beer flavor balance, of course, this is our sulfate to chloride ratio. For beer color, corresponds to residual alkalinity, -100, 0, +100, as guidelines. And for beer structure, soft, medium, or firm, this corresponds to our calcium concentration in the water, 50, 100, 150 as a general guideline. Okay, most beer styles fall in the soft or medium categories. I only know of 2 beer styles that rate a firm style, and that is your Dortmunder Export and Burnt Nails. All right, I am going to take a 30-second break. I'll be right back. Don't go anywhere. Oh, all righty, I'm back. Sorry about that. So, from the Brewcube, I want you to understand this simple relationship between beer color, residual alkalinity, beer structure, calcium content, and beer flavor balance and sulfate to chloride ratio. So your tools for water adjustment are salts, calcium chloride, calcium sulfate, magnesium sulfate, and sodium bicarbonate. And you can see the ion contributions here in 1 gram per 10 liters. You also have a couple of acids that are very common: lactic acid and phosphoric acid. Citric acid can also be used, but citric acid tends to have more flavor impact, which can be good in a hazy IPA where you're looking for some citrusy or fruit-like flavors, but not so good in other beer styles. Here are some suggested salt additions for RO water. These are in grams per gallon. So based on the Brewcube, if you're looking at a pale, hoppy, medium profile, this would be 1 gram per gallon of calcium sulfate, 0.5 gram per gallon of calcium chloride, and that gives you roughly 100 calcium, 150 sulfate, 64 chloride, and a -70 residual alkalinity. You can change that to a more balanced profile with a 1-to-1 sulfate to chloride, or near 1-to-1, by going to 0.75 grams per gallon of each. Again, that same 100-ish calcium. Now you're sulfate is roughly equal to your chloride, the same residual alkalinity level. Pale malty, flipping that around, half gram of calcium sulfate, 1 gram of calcium chloride, and now your sulfate to chloride is flipped around, kind of in a 2-to-1 chloride to sulfate, roughly. Amber, we add a half gram per gallon of baking soda. Dark, we add a full gram per gallon of baking soda, and maintaining the same sulfate to chloride and calcium concentrations. So you can see, water adjustment doesn't have to be complicated. There's no single correct answer for water adjustment either. It largely depends on your taste and your source water that you're working with. These are the results of using those salt concentrations in river and distilled water that we did at one of the BYO boot camp classes. And so we took a pale base malt only grist bill and used both the pale hoppy and pale malty waters, pHs of 5.7 and 5.6. So it brought that, using this -70 residual alkalinity, brought the pH down about 1/10. Using a near zero residual alkalinity, +5 in this case, we were right there at 5.8. It's kind of typical for base malt. And going to a higher residual alkalinity water of +80, that gave us a mash pH of 6.3. Now, as we increase the grain bill, adding 10% crystal and 10% crystal and 10% roast, you can see the pH drop for that dark malty water, 6.3 down to 6.1 down to 5.9. Okay, so this gives you helps you see how varying the water, varying the malt profile can change that mash pH. So how do I adjust water for beer style when I brew? Well, here's my local water here near Los Angeles. I have 40 calcium, 10 magnesium, 120 alkalinity, sulfate, chloride, sodium all around 30 to 40 ppm, and residual alkalinity of +86. So if I put those numbers on the Brewcube, that corresponds to a dark, medium, balanced kind of profile. Okay. But if I want to brew a pale ale, what do I have to do? Well, the first thing I'm going to do is increase my calcium to get that up to at least that 50 minimum for a soft profile, and probably up to medium for a pale ale. So I'm going to add 1 gram per gallon of calcium sulfate, and that changes my calcium level from 40 ppm up to 102. Okay, everything else is unchanged, well, except for the sulfate. The sulfate, of course, goes from 40 up to 187 with that 1 gram per gallon. And this increase in calcium changes my residual alkalinity from 86 down to 42. Not necessarily where I want it to be to brew a good pale ale. It's not going to help me get down to my mash pH target. It's going to help, but not all the way. So if I'm trying to decrease the residual alkalinity, then I need to neutralize that alkalinity with some acid. If I was brewing a dark beer, then I would add alkalinity and add sodium bicarbonate. But for a pale, hoppy, medium profile, I'm going to start by adding 0.75 milliliters per gallon of the 88% lactic acid. And I should add that my water app and other brewing software out there, Beersmith and Brewer's Friend, for example, and Brewing Water, will all calculate or estimate the amount of acid that you need to change your residual alkalinity. So adding this amount of acid brings my alkalinity from 120 down to 3, and changes my residual alkalinity from 42 down to negative 75. So, make sure I'm on the, yeah, okay. So, in terms of actually brewing this water, the first step would be to acidify to neutralize that alkalinity first, then add your calcium salts. One, you want to add that acid, stir, allow that carbon dioxide that's generated to fizz out of the water. That's going to remove that carbonate from the water, and it will also lower the pH of the water, which will encourage and help your calcium salts to dissolve. Okay, so do your acidification first, add your salts second. You're still going to need to stir quite a bit to get them to fully dissolve, but they will dissolve better. In terms of when to add your salts, well, like I said, the first priority is always to achieve your target mash pH. Once you've done that, then you can add more salts if you need to later in the process, say to the kettle. I like to do all of my water additions to my hot liquor tank and then brew with that water throughout the process. But many of you don't have that luxury of having a hot liquor tank that you can change once and brew with. Some of you are doing multiple brews per day, and that hot liquor tank is being partially drained and partially refilled throughout the day, which makes, one addition kind of impossible. Others of you are using instant hot water heaters to supply your water to your brew to your mash tun and your brew kettle. So you may be better off adding your acids and salts to the mash tun, to the specific volume of water that you intend to mash with, and then doing follow-up additions after sparging or to your sparge water or to the kettle during the boil. Okay, again, lots of ways to skin the cat. Now, one thing that has taken more priority in recent years is our understanding of calcium and magnesium for yeast health. If we are brewing with reverse osmosis water and only adding calcium salts, the yeast will not be able to see the magnesium because of all the calcium that's in the way. And this is from, in the water. The malt typically supplies about 30 ppm of calcium and about 70 ppm of magnesium. And that's for a 10 Plato 1040 gravity wort, all malt wort. And so if you add up what's in the water and what the malt contributes, we're trying to maintain some sort of parity, some sort of equality between calcium and magnesium for the yeast's sake. So for example, if we're brewing with a reverse osmosis water and adding the salts just like we did in this previous example, we want to make sure that we add a sufficient amount of magnesium salts to such that the magnesium is at least 40% of the total calcium and magnesium in the wort. So if our water, if we go back to the previous slide, here we have 100 calcium and 10 magnesium. In this example, I've got 100 calcium and 20 magnesium. If the malt is typically supplying 30 ppm of calcium and 70 ppm of magnesium, then the combined total in the wort is 130 calcium and 90 magnesium, and 90 over 220 total is about 41%. So in other words, 90 to 130 isn't essentially equal, but it's in the ballpark. We're maintaining some sort of parity, some sort of equivalence in concentration between the two, and this helps our yeast get the magnesium they need for good, healthy fermentation. Okay, so taking this concept into account of our water adjustment, I'm going to go back and look at this and say, okay, I need to add some magnesium to my water. So I'm at only 10 ppm magnesium. Let's increase that. I'm going to add 1 gram per gallon of magnesium sulfate, Epsom salt, to the water. And that's going to give me 26 ppm of magnesium and 103 ppm of sulfate for that 1 gram per gallon. And doing so, if you go through the software, the calculators, that's going to give you about 290 ppm of sulfate total. A little bit high for a pale ale. Maybe good for a nice strong West Coast IPA or double IPA, but a little bit heavy for a pale ale. So what I'm going to do is I'm going to reduce my calcium sulfate input and rebuild that calcium count using calcium chloride. So I'm going to bring that down. I'm going to do a 0.5 gram per gallon of calcium sulfate, a 0.5 gram per gallon of calcium chloride, and this 1 gram per gallon of magnesium sulfate. And that gives me this concentration. So I'm still at about 100 ppm calcium. I've raised my magnesium from 10 to 36. My alkalinity is still the same at 3. My sulfate has changed from 187 to 217. Pretty comparable, you know, not too different. My chloride has gone up to 99, but in terms of sulfate to chloride ratio, we're still at around a 2-to-1 ratio, which is good for pale ale. Sodium is unchanged, and my residual alkalinity has come down some. Now, depending on your system, your water to grist ratio, this residual alkalinity may be sufficient to brew the beer you want to brew, or you may want to add a little more acid and bring that down further. That's up to you. You know, measure your mash pH with your particular grain bill and see how it comes out. Going back up to generalities, so if we need to brew pale beers, we generally want to neutralize alkalinity. And this is pretty easy to do. You look at your total alkalinity and divide it by 50 to get milliequivalents per liter. So for example, if you have a total alkalinity of 150 ppm as calcium carbonate, divide by 50, that equals 3 milliequivalents per liter. You would then add 3 milliequivalents per liter of acid to neutralize that alkalinity. And these calculations are in both How to Brew and in the water book. And so you can make a 1 normal concentration acid solution using 85 milliliters of lactic acid and bringing it up to 1 liter of solution. And that makes those acid calculations very easy. Again, your mash pH target for pale beers is generally for 5.2 to 5.4. If you're going to add alkalinity to brew dark beers, low mineral water needs alkalinity to buffer your dark malts. So sodium bicarbonate works better than calcium carbonate. It reacts much quicker, dissolves more easily. Hydroxides work even faster, but and this could be calcium hydroxide, which is known as pickling lime, or it could be sodium hydroxide. But hydroxides tend to have a chemical taste, according to people that have used them. So I think sodium bicarbonate is your best bet for adding alkalinity to brew dark beers. The additional sodium is not a big deal. It helps accentuate the malt character of the beer. Again, don't try to make everything both hoppy and malty, because then you do start tasting minerally. 50 to 75 ppm as calcium carbonate alkalinity for your red and brown beers, 75 to 125 for your brown to black beers. The particular amount of residual alkalinity needed depends on the depth of that color. Exactly how much, uh, specialty and roast malts you're putting into that recipe, as well as the original gravity of that style. You know, an imperial stout is going to need more buffering than a regular Irish stout. Makes sense, right? Mash pH target again, a little higher end of the range, 5.4 to 5.6 as a guideline. If you are adjusting your sparge water, your target mash pH is your first priority. The next priority during sparging is to prevent pH rise. You don't want to exceed 5.8 because that tends to promote astringency. So a lot of brewers add acid to the sparge water when brewing pale beers to prevent this pH rise. And what I want to say is, don't acidify your sparge water based on its pH. Acidify it based on its alkalinity. In other words, use the total alkalinity number and the calculations I showed you a couple slides back to reduce that total alkalinity to 0, to exactly neutralize that alkalinity. If you find, depending on your particular grain bill, you need a little bit more acid, fine. You can add a couple more milliliters. But, don't just dump in a bunch and assume you can't go overboard, because you can. All right. Also, you don't need to add alkalinity to your sparge water when you're brewing dark beers. You've added the alkalinity to the mash to buffer the pH of the mash to keep it in that 5.4 to 5.6 range. But if you sparge with alkaline water at this stage, you'll eventually start seeing that pH rise again, and you don't want that. So don't add alkalinity to your sparge water for dark beers. If you sparge with, regular low alkalinity water or reverse osmosis water, no alkalinity, your pH won't rise. The dark malts in the mash are going to keep that running's pH low and avoid astringency. Different options for managing sparge. If you have a large hot liquor tank that you can adjust ahead of time and brew and sparge with that, great. Always monitor your runnings pH. Make sure that and taste your final runnings as well. That's a good way to catch if your pH, if you don't have a pH meter and you're worried about astringency, just taste your final runnings. You can taste that astringency there. Generally, I recommend using low alkalinity water for sparging with. Add salts as needed to the kettle. And acidify your high alkalinity sparge water to neutralize that total alkalinity or residual alkalinity and to 0, and add salts as needed to the kettle. Okay. I'm sure there'll be some more questions about that later. In summary, we adjust our water to achieve our target mash pH. We also adjust our water to adjust our beer seasoning to help the beer's flavor balance and support the beer's flavors. Brewing is cooking, okay? There's no single correct answer. Classic brewing cities, classic brewing styles, guidelines, okay? Don't oversalt your water, but don't be afraid to adjust it to your taste. And with that, I can take some questions. If you have further questions after this talk today, feel free to email me at john@howtobrew.com. Aaron?
All right. Just a reminder, if you do have a question currently, you can use the prompt at the bottom, ask a question. And if there's one that's already been asked that you would like to know the answer, you can vote it to the top so that we can get to that. So I will begin with this one from Arthur. For the 3 common water additions, calcium chloride, calcium sulfate, and magnesium sulfate, is the mash the best place to add them, or do any of them work better being added to the hot liquor tank before mashing or in the kettle post-mash?
Good question. I like to do my water additions to the hot liquor tank. So just like if I was holistically brewing with natural water in the first place that had the right, mineral concentration. That being said, um, calcium chloride dissolves in water easily. Calcium sulfate dissolves slowly. Magnesium sulfate dissolves pretty quickly. But calcium sulfate, gypsum, dissolves slowly. It dissolves better in cold water than in hot water. So, um, and again, this is why I recommend if you're going to be acidifying, acidify first, because this will aid the dissolution of the calcium sulfate. Um, adding adding salts to the mash after you've doughed in, they will dissolve better, but you have the problem of distribution and homogeneity. Okay, so if you're going to add your salts to the mash after you've doughed in, you need to stir really well, get them really well distributed. Otherwise, you're going to have different pH values around that mash. All right, so again, that's why I like to do my water adjustment before I dough in.
Okay. And then the next one from Trent. Is it better to start with 100% reverse osmosis water and build the water profile up, or to use tap water and adjust the water profile?
Another good question. It depends on what your tap water is. If your tap water is really high in alkalinity, and when I say really high, I mean over 150, it may be better to start off with reverse osmosis or distilled water. Depends on the beer style you're brewing too. If you remember back to my LA water, it's 40 calcium, 10 magnesium, 120 alkalinity. I use that water for brewing all of my pale ales and darker beers and so on because it has a bunch of what I need. And it's easy to adjust if I'm brewing like an amber versus a dark with a little bit of acid addition. If I'm going to brew like a Munich Helles or a Kolsch or another light beer, very pale beer style, then I start with reverse osmosis water.
All right. And then the next one from Gord. I use RO and distilled water interchangeably, but are there differences that I should know about when I'm building brewing water?
Your distilled water generally has lower mineral concentrations than RO water. RO water varies depending on whether it was a single stage, double stage, or triple stage reverse osmosis system. The triple stage will be the most pure, the lowest mineral concentration. Single stage, you're going to get roughly 10 ppm of most of your ions and maybe 20, 30, 40 ppm of alkalinity in that water. And remember that when we're talking about brewing and brewing water, if the concentration is less than 50 ppm, it's below flavor threshold. It's a low concentration. So in my view, reverse osmosis water is close enough to zero because we're going to add, 50, 100 ppm worth of salts to that water for any other, for any particular ion. So it's going to kind of swamp out what was there in that reverse osmosis water. So I really don't care if it's 10 or 0 ppm in the reverse osmosis water. I'm going to add more. And so it's a consideration, but I don't think a terribly important one.
All right. Kane would like to know, at what point water quality would you think it would be necessary to install an RO system?
Okay. Again, a good reason to install a reverse osmosis system is your alkalinity is very high, and you need to knock that down. And by very high, I mean over 150, over 200 ppm. If you are a professional brewer and trying to brew consistently with changing water supplies, and your alkalinity varies between 50 and 100, month to month, then yeah, I'd recommend an RO system just to take that variability out of the mix. If you're at home, if your alkalinity is 100, 100 to 150, that amount of alkalinity can be worked around. I don't necessarily recommend an RO system. Distilled water, $10 of water from the grocery store may be a cheaper option in the near term versus, say a $200 RO system that you put under the sink, for example. But those are the considerations that I think you should ponder in deciding whether to buy one or not.
Okay, Jeremy, what are the least forgiving styles when not adjusting your water profile?
Least forgiving styles. I would say your light lagers. Your light lagers, American lager, Kolsch, Helles, Pilsner. If you have high alkalinity, your pH is going to be off, and it's going to make those beers taste dull or even harsh. Darker beer styles are pretty forgiving when it comes to not adjusting your water. The malts, the malt buffering power will keep the pH in the ballpark pretty well. The thing you can run into with dark beers is that the pH goes a little too low. Your yield can be less if it drops below 5. Your malt character may not be as complex as you hoped if the pH goes below 5, but it'll still be beer. It'll still be quite drinkable. But yeah, your lighter styles, your lighter, paler styles are the ones that where water adjustment and mash pH are more critical.
Okay, Philip, could you explain when/how chlorine interacts with the brew? If chlorine boils away, wouldn't it boil away when the wort boils, or is it too late by the time you've mashed with it? Thanks.
So chlorine can chemically react to form chlorophenols. And chlorophenols are this medicinal or Band-Aid or sticking plaster, bandage kind of aroma. It's kind of a plasticky aroma that can be. I've actually had beers in competition, not that I brewed, but I'm tasting, judging, that have had a very pronounced chlorophenol aroma. And so, if you want to get that chlorine and chloramine out of your brewing water before it contacts the mash and has a chance to react and form these chlorophenol compounds. So if you have a hot liquor tank and you heat up the hot liquor, chlorine will vent and boil away if you give it time. Chloramine won't. And so that's why I recommend your chemical methods, either, carbon filtration. If you're using carbon filtered water, then the chlorine will be reduced or removed, or the sodium metabisulfite or vitamin C additions to neutralize it and turn that chlorine into chloride, which does not form chlorophenols.
Okay, and I think just kind of on that, Kane, also, I think you answered it. Also, how does chloramine react? Is it anything different?
Yeah, it still forms these chlorophenols. The difference is the chloramine doesn't get boiled away. It has a much lower vapor pressure, and so it sticks around from the hot liquor tank and reacts in the mash.
All right. How best to measure RA in mash at kettle full, at knockout, and in finished product to gauge how well targets are being achieved? Are there low-cost benchtop methods versus sending samples off to labs for analysis?
How to measure reverse us, sorry, how to measure residual alkalinity. Okay, in the mash. Um, well, residual alkalinity is a calculation. It is the amount of alkalinity in the water versus the hardness in the water according to that equation. So you measure it by calculating it with brewing software. pH is what you actually measure in the mash kettle full knockout finished product. And so, yeah, residual alkalinity is a factor for pH. And that's why we talk about residual alkalinity and why I talk about water adjustment with residual alkalinity. But it is because it is simply a factor for pH, and pH is what we measure. Does that answer that? And low cost benchtop, well, the low cost benchtop method for measuring residual alkalinity is that water test kit I showed you earlier in the presentation. That's, you measure it by measuring the calcium and magnesium and alkalinity of the water sample. You measure the results of your water adjustment as pH at each stage of the process. And for that, you need a pH meter that has 2 decimal point resolution, and those generally cost about $100.
Okay. How much water adjustment can actually be done on the fly / during a brew day to bring water and wort closer to ionic and pH targets?
Some. Not a very good answer. It's relatively easy to add acid to the mash, to add some more lactic acid, to add some phosphoric acid or citric, to bring mash pH down a couple tenths. That happens fairly quickly, 10 minutes or so, and you can see the result. Raising mash pH is more difficult. If you have a strong base like calcium hydroxide or sodium hydroxide, you can do it within the same 10, 15 minute time period. If you're adding baking soda to the mash and stirring that in, that's going to take longer, 20 to 30 minutes to have an effect. And you've got to stir enough to get it homogeneous. And so this is why I recommend treating your water ahead of time in the hot liquor tank and then doughing in, because now you've got a homogeneous mash with a homogeneous pH.
All right. And then Dan would like to know, can I add my salts and acid additions the night before when I collect my water and set up for an early morning brew day?
Yeah, you can. The one caveat to that is, you acidify your water, you drive down the alkalinity, you stir, you vent that carbon dioxide. The water is going to start reabsorbing carbon dioxide in contact with the air. So, overnight, not a big deal, but if you let it sit for a couple of days, you may be right back where you started in terms of the amount of alkalinity in the water. So that's one little thing to be aware of. But yeah, in general, you can do it the night before and brew the next day.
Great. Bill would like to know, does 5.2 pH stabilizer work to adjust hard water?
Tricky question. 5.2 pH stabilizer works by adding phosphate buffer to the mash. And hardness isn't the problem. Alkalinity is the problem. So yes, it works, but it may not be the solution your water actually needs. And I don't want to denigrate a good a good 5-star chemical product, because I really do love 5-star chemicals products, but 5.2 is not the wonder drug, wonder cure for all your water problems. Understanding water and what each of the ions does and brings to the table is a better solution than the 5.2 Band-Aid.
We support that as well, John.
Okay.
We definitely support that.
Good.
It is not a cure-all for everything.
Exactly. Yeah.
Okay. Kane would like to know, how can pure RO damage brewing equipment and what precautions should be taken to prevent it? Is there a general TDS range?
Yeah, good question. Reverse osmosis water, specifically, or more specifically, distilled water with no minerals in it, is very corrosive. And when I say corrosive, I mean it's going to leach ions into itself. It's it's the universal solvent. So yeah, when we make reverse osmosis water, when we store a high purity water, we do it in plastic or non metal tanks because to prevent corrosion. That being said, you don't need a lot of mineral in the water to mitigate that effect. If you think about Seattle water, that's not particularly corrosive. So a little mineral, say one equivalent of each, 10, 20 ppm of each ion, will prevent your reverse osmosis distilled water type corrosion on stainless steel. Corrosion is a really big field, lots of factors. So it's hard to generalize too much without really having to get into specific cases. But yeah, in general, low mineral concentrations, 10 to 20 ppm, will mitigate that kind of corrosion.
All right. If all malt wort contains 70 ppm magnesium, then is there any need to ever add Epsom salt?
There can be, because again, what we're trying to do is maintain some sort of equality, some ballpark equality between the amount of calcium in the water or in the wort and the amount of magnesium in the wort. So the yeast, when they are looking for these nutrients during fermentation, don't just see a wall of calcium in front of them. They see roughly equal concentrations. So again, if you're going to brew with reverse osmosis water and you're just adding calcium salts, and if you're adding 100, 150 ppm of calcium salts, you may not be giving enough magnesium to maintain that parity, once you add in the malt contributions and the water contributions. Plus, this 70 ppm is kind of like one data point or maybe a couple data points. I don't know how typical that number is. Barley is an agricultural product, and the minerals that are in that barley, that come out of that barley into the brew, depend on where it was grown, how it was grown, and the climate at the time. For example, Ballast Point did an interesting presentation a few years ago when they were looking at chloride levels and trying to adjust the sulfate to chloride in their final beer, and realized that they were getting 200 ppm of chloride just from the malt. And then they examined different base malts from around the world and found quite a range, anywhere from 100 to 250 ppm of chloride was coming from the malt itself, depending on what region it came from. So I imagine that there's that same kind of variability in terms of magnesium as well. Kind of stands to reason. So again, as a consideration when you're doing salt additions, try to add some amount of magnesium just in case.
All right. When adding chemicals to the boil, gypsum and calcium chloride, how do you figure the water amount to treat?
Yeah, if you're able to measure your water additions, um, then I would, and so you've you've done a specific amount of water for the mash, specific volume for the mash, and then you're going to sparge with another amount. Then I would add sufficient salts to make up for that sparge volume. That's what I would add to the kettle. If you go over a little bit or under a little bit, not a big deal. Again, this is not critical. It is, the thing's not going to blow up or melt down on you. It is simply you are adjusting, flavor aspects. A little more, a little less isn't going to really matter. The important work was done in the mash. That's where pH and so on is critical, because you're trying to get the best conversion and the best wort from the mash. Now that the wort's in the kettle, now we're just kind of worrying about flavor aspects and that sulfate to chloride and so
on. All right. Will they be able to download the slides of the presentation?
I believe so. I mean,
okay.
Well,
if you make them available, I'll make sure everyone gets them.
Okay.
Or some version of them for people to reference. Does that work, John?
Yeah, I'll send you a PDF later.
Great. Yeah. So to answer that, with the follow-up email with the recording of the session, I'll also send a link for everyone to download this presentation.
Okay.
Let's see. On RO water, is there a set amount of 10% phosphoric acid per gallon or liter can keep it simple? So many milliliters of phosphoric acid per liter ratio or ounces per gallon?
No, there really isn't a single answer to that, because again, it's not for RO water, it's not the pH of the water that matters, it's the pH of the mash. And so the pH of the mash is going to depend on what malts are in that mash and how much water you're adding and so on. So yeah, I really can't say how much acid you may want to add per liter per gallon to be the right amount. It really depends on the recipe.
All right. Do you have any thoughts on Burton water salt sold by the LHBS? Have you used in your brewing as a kettle salt?
I haven't used that product. So I don't know exactly what's in that compilation, Burton water salts. Again, look at your water, look at your source water. You can test it with the Brew Lab water test kit, or you can send it off to Ward Labs, for example, to have it tested and tell you what's in it. If you're brewing with your tap water, you can look at your city water report and see what the general average ion concentrations are, and then add the different salts to build that water up to where you want it to be. The Burton water salts are probably best added to distilled or reverse osmosis water. I assume that they designed those to have a nominal concentration added to reverse or distilled water.
All right. Is 100% RO water the same as distilled water? What is the difference, if there is any difference?
Yeah, the difference between the two is the amount of residual ions in the water. Distilled water, by definition, is supposed to be completely mineral free. Reverse osmosis water, like I said, varies anywhere from 0 up to 10 to 20 ppm, depending on the individual ion. Reverse osmosis water, though, is generally very low in minerals, and I consider that amount to be negligible when it comes to salt additions.
So, as a rule of thumb, don't blindly add the pH 5.2 stabilizer at the beginning of the mash.
Yes. Correct. Measure your pH and add some 5.2 stabilizer. Measure pH again. Maybe add some more. Measure again. You know, you're trying to get in that ballpark, and you're trying to manipulate that ballpark a little bit depending on the beer style you're brewing. But you know, the amount of pH change with the 5.2 stabilizer is going to depend on the grain bill and the water to grist ratio.
All right. James would like to know, using RO water, I build my profile to the style I am brewing. Once I've added water salts, I've adjusted water pH with lactic acid down to at least 6. You seem to be recommending not doing that until 10 minutes following dough in. Am I understanding that correctly? If so, why?
Okay. Again, when you adjust the pH of the water, you're acidifying it, yes, but the pH of the water doesn't matter. It's the pH of the mash which affects the enzyme activity. That's what's important. So RO water has no buffering, in it. It doesn't have very much alkalinity to buffer mash pH. So you can add salts to that water, the calcium, magnesium, sulfate, chloride. That's fine. Then you need to dough in and see what your mash pH is, and then acidify to drive that pH down if that's what you need to do. If you use the brewing software, if you use my water calculator, and are targeting a specific residual alkalinity with regard to your grain bill, and again, this kind of goes back to the Brewcube, selecting beer color versus residual alkalinity, or using Beersmith or Brewing Water to target a specific mash pH, then those calculators are going to determine these salt amounts and these acid additions for you, so you're not just kind of doing it by adding a little bit and seeing what you get.
So Gary would like to know, so we use these cheap pH meter sticks to measure pH. Are these reliable, or should we invest in a better quality meter, and should we buffer at 3 different pH points?
You definitely need to not use the pH test strips. They aren't reliable. And like I said, a good pH meter will cost you about $100. And you only need 2-point calibration, your pH 4 and pH 7 buffers. That will calibrate you on either side of the mash pH range. And that's what you need.
All right. Dylan would like to know, if you aren't worried about 1 to 10 ppm after RO, does that mean that the water dispensers you find at supermarkets would be a fine water source, or should you stay away from those since we don't know how long it's been since the filters were changed?
Yeah, I kind of avoid those since you don't know how long it's been since the filters are changed. If it's kind of like malt extract. If they go through a lot of malt extract, that it's pretty fresh. If you see that water dispenser at the supermarket getting lots of use and being recharged regularly, and then they have a inspection sticker on it, then yeah, it's probably fine. Otherwise, I would go inside and buy the 2.5 gallon jug of distilled. Those aren't very expensive, and that's what I do when I'm brewing these lighter beer styles.
All right. Water pH is not important for the mash. What about dropping the pH of sparge water?
Again, don't acidify your sparge water based on pH. Do it based on the alkalinity of the water. Again, if it's tap water, you can get that from that number from the city. If you have a brew lab or other test kit, you can measure it yourself and acidify according to that alkalinity. You can acidify your water down to 5.2, you know, putting the cart before the horse, as I said. Probably pretty safe, but again, I would rather do it based on the amount of alkalinity in the water rather than pH.
Okay. Let's see. Does Brewing Water use the cube methodology? Would you recommend it as a way to adjust water?
I would recommend Brewing Water as a good program to use. I'm not sure if he uses the cube methodology. I think Martin and I have kind of done our own thing in parallel. We have much the same understanding of water, so I'm not. I use my stuff, he uses his stuff. So I'm not really sure how closely it parallels, but yeah, I do recommend it. It's a good program. I find it, when I've looked at it, to be a little more complicated than my own water spreadsheet and water calculator app, but lots of people use it and have very good results with it. Same with Beersmith.
Okay. If you don't have an RO set up, thoughts on using distilled?
Yeah, if if you have distilled available, that's what I do when I'm brewing these light beer styles. So yeah, 20 gallons of distilled isn't that expensive. I mean, for a home brewer, it's 10, 15 bucks perhaps, but whatever.
Where can I get my tap water from Colorado Springs, Colorado, tested to see how I should adjust? Is that something the city water department should be able to give me?
Yes, if you call up your city, your water supplier, ask them for test results. So very often, the water quality reports that you can get online from the city won't have all the info for the 6 ions that we're interested as brewers. They focus mainly on the federal requirements for clean water, which are chemicals and pollutants and so on, making sure those and bacteria are 0. So you may get calcium, you may get alkalinity, but you may not get the magnesium, or you may not get the chloride that you want. So yeah, just calling the city will usually get you that info.
Okay, and then I think there was one over here on the side. When using brewing software like Brewfather to calculate the water salts additions, it's supposed to take into consideration the grain bill of your recipe. Is that correct? I mean, we can add the calculated salt the software recommends.
Yes. Software that includes the grain bill and estimates the alkalinity and acidity of the grain bill based on the weights and so on. That's helpful, but I don't think there's, at least the last time I looked, there's not a lot of published data on specific malt alkalinities and acidities. It's an estimate, it's a model. So as far as I know, those calculators work pretty well. They get you within plus or minus 1 or 2 tenths to your final mash pH in terms of that estimate. But my own calculator only goes as far as the water itself and the residual alkalinity. As you brew more and you gain more experience, you'll start developing kind of an understanding of how acidic a particular grain bill is, and you really don't need to rely on the software to calculate it for you.
Okay, and I think that those are all the questions that we had. Once again, thank you for everyone who joined us. Thank you to John, and I will be sure to get out the presentation and the slides provided by John. Just a reminder, if you'd like to contact him, that is also on the presentation. So thank you for that, John. And our next presentations, in May, we will have BSG with developing recipes with fruit, And then in June, On Tap will be joining us to talk about Brewery Financing 101. So once again, thanks for joining us, John, for the great presentation, and thank you for all the attendees. Have a great day.
Thank you.